Hi everyone. In this session, I'm going to start off by looking at continuous random variables and then move on to the normal distribution. As always, the first step will be to look at the outcomes. You need to know the definitions. You need to know the properties of the normal distribution, the t and the sampling we'll get to in the next section. You need to be able to solve problems using these distributions, and you need to be able to distinguish between when to use these distributions with the various problems. Right, now just quickly to start off with a bit of revision. A random variable is a function that assigns a real number to the outcomes in the sample space. In the case of a discrete random variable, we have a countable number of outcomes, and typical examples of this will be the Poisson distribution and the binomial. With a binomial, the number of successes that we can count in n trials can be as little as 0, but it could also be as much as n, which is the number of trials. If we look at the Poisson, then the number of events that would occur in a specific interval or area or space can be as little as 0, but it can also be infinitely many. So even though it's infinitely many, we're still able to count it, or that will take a long time. So that's the main property of discrete random variables, is that the number of outcomes is countable. In the case of flipping a fair coin 3 times, over here with flipping a fair coin 3 times, the sample space will consist of outcomes that has heads and tails. Now it's a non-numerical outcome, so what we'll do is we'll define our random variable x to equal the number of tails. So that means that x will start at 0 and end with 3, because we're counting the number of tails in the 3 flips of a coin. The probability for each one of those will be given by the probability mass function, or the PMF, and then the cumulative probabilities where we add together will be given by the CDF, in other words the cumulative distribution function. Now the probability mass function, or PMF, is a bar graph where each bar represents the probability of that specific outcome, 0, 1, 2, and 3. Okay, and the height of the bar will be the probability, but because the width of each bar is equal to 1 unit, the area of each bar will be equal to the probability as well. The CDF is a step function. In this case, when we have x equal to 0, the probability is equal to 1 over 8. So from 0, the probability is equal to 1 over 8. Then at 1, you'll see that there's a circle there. That means it's discontinuous. It jumps up to 4 over 8, because at 1 we have an additional 3 over 8 probability that's added to 1 over 8, so that gives us our 4 over 8. And then it'll stay at 4 over 8 until we get to 2. Then at 2 we'll add another 3 over 8, and that will give us 7 over 8. So this is the 7 over 8. And then at 3 it jumps up by another 1 over 8, so that will give us 1, etc. Right, but the important thing is, in the case of a discrete random variable, our CDF is a step function. Now for continuous random variables, we have uncountable number of outcomes. Now an uncountable number of outcomes simply means that we cannot count it. Okay, that's exactly what the name says. There's too many to count. So if we look at what it means regarding our distribution, then we're not going to be looking at specific outcomes, because there are too many of them. We'll be looking at intervals. So for example, you'll have an interval a0 to a1, where a0 will be the smallest value and a1 will be any other value. Then from a1 to a2. So this is very similar to what we did when we constructed the frequency table from which we constructed our histogram. In continuous data, using Sturge's rule, we created these intervals. So this is similar to that. Now because we have uncountable many outcomes, the probability of a specific outcome will be equal to 0. And we can see this if we think of the concept of uncountable outcomes. If we have an event, then the probability of that specific event, if it only contains one outcome, will be 1 over the number of outcomes in the sample space. So in this case, the number of outcomes in the sample space is uncountable, so that means that we'll have 0. Right, so this is the idea behind it. It's not exactly like it is over here, but this is the idea. So this is why the probability of each individual outcome will be equal to 0. So we have to look at intervals. So that means we'll take the probability of this interval, probability of the second, the third, etc. And then Because we're looking at intervals now, not specific outcomes anymore, the name changes from a PMF or probability mass function to a density function. In other words, a PDF. Right, if we look at the cumulative probabilities, then the idea is exactly the same. We'll simply add the probabilities up to a specific point, and that will be denoted by a capital F, and we'll simply plug in the value up to which we want to add all the probabilities. So in this case, f of a1 will be all the probability up to a1. Of course, if we look at the probability up to just before a0, then there's going to be nothing, because a0 is the first value that actually will contribute towards the total probability. We still call this the cumulative distribution function, in short, the CDF. Graphically, we have for the PDF a continuous curve, not like the bar graph we had for the PMF. This is a continuous distribution, so we have a continuous curve. If we want to calculate probabilities, then we look at the area underneath the curve between specific values. So let's say A2 and A5. And the way in which we calculate those probabilities of that interval will be by integrating the PDF, which we denote by f of x. You should recall that the PMF is denoted by px. Okay, but in the continuous case, the probability density function will be denoted by a lowercase f of x, whereas the CDF is always denoted by a capital F. Right. Speaking of our CDF, it is also a continuous function. There's no jumps, there's no discontinuities, because this is a continuous random variable. It's just going to be a smooth curve from the lowest point, which will be 0 for a specific value of x, up until the highest point, which of course will be 1 for the largest value of x in our distribution. If we look at calculating probabilities using our CDF, or our cumulative probabilities, then we need to be able to subtract. Because if we want to calculate the probability of being in this interval a2 to a5, then what we'll do is we'll look at the total probability up to a2 using our CDF. We'll look at the total probability up to a5, which is this blue area, and then we will subtract the one from the other. So we'll take the total up to a5 minus the total up to a2, and that's going to give us the probability of being between a2 and a5, which is the same result as what we'll get when we integrate from a2 to a5. The other very useful property of a CDF is finding that of percentiles. Right, so let's say, for example, I'm interested in separating the top 20% of the data from the bottom 80%, then I'll look for 0.8 on my vertical axis. In other words, I'll look for 80%. Okay, the 0.8 means that this is the point where up to where I've accumulated 80% of my data. I'll move across until I cut my CDF curve, and I'll move down. So that means that I've now isolated 80% of the data on the left, in other words the smallest 80%, and that will be my 80th percentile. Right, now the properties of the PDF and the CDF. For the PDF, we have f of x, which is at least 0. Now f of x is the function that gives us this curve over here. Now please note that the shape of this curve is just an example for the sake of illustration, but this curve can have many other different shapes. So f of x is what defines the shape of this curve, but please note that it is not, I can't stress this enough, it is not a probability. The property is that it is greater than or equal to 0, but it can actually be greater than 1. The probability comes from integrating. So when we integrate from a point A to a point B for this function, then we will actually determine the probability. It's the area under the curve. Right, and then of course if we integrate the entire area, or the entire support of our random variable, then we'll get 1, because that will be the total probability. For our CDF, as x becomes smaller and smaller, the cumulative probability will be 0. If x becomes bigger and bigger, the cumulative probability will be 1, which makes sense because the further we move along the x-axis, the more probabilities we accumulate until we eventually reach 1. And then lastly, if we want to find the probability between 2 points A and B, then we simply take the total up to B, we'll subtract the total up to A, that is if A is less than or equal to B, which we saw in the previous illustration. Right, so this was a very brief introduction to continuous random variables. The two main forms, which will be the PDF and the CDF, their properties, and how we can use each one to find probabilities. Now in our case, we're not going to be using the PDF to find probabilities because it requires integration. We're only going to be looking at distributions, or continuous distributions, where we can use cumulative probability tables, like what we did in the discrete case for the binomial and for the Poisson.